Good morning, students. Today we will discuss about the adjoint and inverse of a matrix. Now, adjoint matrix of a square matrix is denoted by adjoint A, and it is formed with the help of cofactors of all these elements of the matrix. But you know, cofactors, in case of determinants, you have derived it. Let A be a square matrix of order 3 by 3, and if we replace all these elements by their corresponding cofactors, the matrix formed is called cofactor matrix. So, you vectors of all these elements and replace each and every element by their corresponding cofactors, then it will be a cofactor matrix of that. Now, adjoint of this matrix is the transpose of the cofactor matrix. Mean row column will be interchanged. So if capital Aij is the cofactor of the element small aij, then cofactor matrix will be capital A11, A12, A13 like this. And adjoint A is the transpose of that cofactor matrix C, which is A11, A21, A31, A12, A22, A32, and third row is A13, A23, A33. Now let us take an example of order 2 by 2. Suppose A is equal to 3 minus 4, 5, 6. We have to find out adjoint of this matrix A. First we will find out cofactors of all these elements. A11, cofactor of the element 3 is equal to 6. Cofactor of the element A12, which is capital A12, you can write in this way, minus 1 to the power 1 plus 2 into minor of that element, which we know in the chapter determinant, that is equal to minus 5. And similarly, A21 is equal to 4, A22 is equal to 3. So cofactor matrix we have got, that is we call C, is 6 minus 5, 4, 3. Now adjoint of this is equal to C transpose, which is equal to 6, 4, minus 5, 3. Similarly, another example of a matrix A 3 by 3 order is given. Here, if you find cofactors A11, cofactor A11 is equal to minor of this element because it is in even place. So M11, which is equal to 2, 3, 1, 1, which is equal to minus 1. Similarly, A12, which is equal to minus of M12, because you know in odd places, minor cofactor is the negative of the minor of that element. So similarly, we will find out all these minors and corresponding cofactors. Then you will get cofactor matrix, which is equal to minus 1, minus 8, minus 5, 1, minus 6, 3, and minus 1, 2, minus 1. So adjoint of this matrix is equal to C transpose is equal to minus 1, 1, minus 1. 8 minus 6, 2 minus 5, 3 minus 1. Now there is a theorem which says that A into adjoint A is equal to adjoint A into A is equal to determinant A into identity matrix of that order which is of A. If A is a square matrix of order n, then you can say A into adjoint A is equal to adjoint A into A is equal to determinant A into I, where I is the identity matrix of order n. Now first we will find out the adjoint matrix of A, which is transpose of the cofactor matrix. So it is A11, A21, An1, and A12, A22, An2, and the last row is A1n, A2n, Ann. If we multiply A into adjoint A, here you have to remember when elements of a particular row is multiplied by the corresponding cofactor and it is added, algebraic sum of the products of elements of a particular row with their corresponding cofactor gives the value of the determinant. You know it from third order determinant's value. But if elements of a particular row are multiplied by the cofactors of any other row, then added algebraic sum of the products of elements of a particular row with the cofactors of any other row will give you 0. So here after multiplication you will get diagonal elements are determinant A and all other elements will be 0. So after product you will get determinant A 0, 0, 0 and second row is 0, determinant A, all are 0 and only diagonal elements will be 0. Diagonal elements will be determinant A. So if you take the common factor determinant A, it will be an identity matrix of order n. So it is determinant A into I. Therefore, you can say A into adjoint A is equal to adjoint A into A is equal to determinant A into I. Here we have another definition which is non-singular matrix. I think we have told in chapter Determinant. Non-singular matrix is a square matrix whose corresponding determinant value is not equal to 0. And when the determinant value of a matrix, square matrix, is 0, it is called a singular matrix. Now, invertible matrix. A non-zero square matrix of A of order n is said to be invertible if there exists another square matrix B of order n such that AB is equal to BA is equal to I, then A and B are said to be inverse to each other. So you can say A inverse is equal to B or B inverse is equal to B. It is already discussed in elementary row operation, and using that elementary row operation we have derived inverse of a matrix in the previous chapter. But again we recall it. So if we use the formula A into adjoint A is equal to adjoint A into A is equal to determinant A into I, and divide this throughout by determinant A, because determinant A is not equal to 0 as non-singular matrix. So you will get A into 1 by determinant A into adjoint A is equal to 1 by determinant A into adjoint A into A is equal to I. So you can say AB is equal to BA is equal to I, where B is equal to 1 by determinant A into adjoint A. So you can say A and B are inverse to each other, and A inverse is equal to B, which is equal to 1 by determinant A into adjoint A. So remember this formula, the A inverse is equal to 1 by determinant A into adjoint A. An example is given here of 2 by 2 order determinant, 3 minus 5 minus 1, 2. Here if you find determinant A, which is equal to 1, not equal to 0. Now we will find out, we can find inverse of this matrix because it is a non-singular matrix. So we will find out adjoint A. Adjoint A, to get adjoint A we need cofactors. So we can find out cofactors A11 which is equal to 2, A12 which is equal to 1, A21 is equal to 5 and A22 is equal to 3. So adjoint A is equal to transpose of this cofactor matrix which is equal to 2, 1, 5, 3 transpose which is equal to 2, 5, 1, 3. Now you can say A inverse is equal to 1 by determinant A into adjoint A is equal to 1 by 1 which is equal to 1 into the matrix 2, 5, 1, 3. So it is equal to 2, 5, 1, 3, that is A inverse. It is not necessary the determinant value is always 1. In other cases that 1 by that much will remain as it is. No need to insert it. So here we can derive inverse of a 3 by 3 matrix also, but in the next class we will discuss. Thank you.